Good morning. By a show of hands, how many of you tried to buy the book with the code and it didn't work? Yeah, okay. You're not alone. Our other classes are having trouble too, so we're trying to sort that one out. In the meantime, do the grace period, right? The free 14 days. And we'll try to get either a different code or get them to turn the codes on their end or whatever has failed. We'll try and get that fixed. But got several emails in yesterday and today about that, and we're waiting to hear back. So just hold out on that one. If you've already paid, you're all fixed up. Let's see here. Lab tomorrow, right? I always try to do the beginning of class to get the administrative stuff out of the way. We've got lab tomorrow. You're going to be there the entire time. Prepare yourself mentally and emotionally and physically for for boredom, because there's lots of additional information about the syllabus and working with Wiley Plus, and we got to ram through that. And again, I haven't figured out an interactive way to do that. And then I'm going to give you a math preview in the form of some problems for you to see if you know how to finish the math, right? And that's going to be that's going to be like a self-test for you, okay, as to whether or not mathematically you are okay or not for this course. So that's what we're doing tomorrow, and it's going to take the entire time. All right. Hopefully, I've gotten a few people saying that can't get into Canvas, that sort of stuff. We've been sorting those things out via email. If you're still having trouble, make sure that you come in on Friday to GRASP, and we can really nail down. I really don't want to do any technical support after Friday. Of course, I will, but I'd literally like to have everything ready to go by Friday, because we're in the course. Homework is due and all kinds of stuff. When is your first homework due?
Saturday.
This Saturday?
Yeah.
18th. Okay, I'm going to fix that. Because we're still, I haven't told you all about Canvas, and I don't want to turn around and have you turn in stuff in 2 days. So. I'll forget that. Remind me tomorrow. All right. I asked you to go kind of, review unit conversions, that sort of stuff. I seem to remember you telling me that you had you needed some sort of conversion factor, right? To be able to pull off any kind of unit conversion. Where do you find conversion factors?
Internet.
Internet. Okay. Google. Get your calculators out and give me a random number. Somebody. 25.32. Okay. So we have 25.32 feet. Okay. And we want to get this into meters. So how do you do that? Hey Siri, what's 25.32 feet in meters?
25.32 feet is 7.72 meters.
This is how it's done, right? Why have brains anymore? Because they're all in these boxes, right? But if we're going to understand the underlying mechanism of what's going on here, we need to be able to communicate, to talk, to convert from one unit system to another. So we need this conversion factor. We can get them from the internet, we can get them from the book, and when I give you a test, I will give you the conversion factors. Okay? They will be on the exam, and if they're not on the exam, then I will give them to you right there. You'll just come up and ask me, because I don't want you wasting time writing down conversion factors. I did realize I forgot to do one thing. There is need for note takers in here. These are, what happens is if you're taking notes on paper, we will give you some carbon paper, the ancient 1960s Xerox. And you'll put that in there, and as you take your notes, a copy of them will just go magically through to the next paper down, and then you hand that off to the individual that needs the notes taken for them. So if you are interested in that, please come up right after this class. I have a need for 2 individuals in this class for that. You get all kinds of different perks. I don't get any money, but I think you get priority registration and all that sort of stuff. So if you're interested, let me know, and we'll take care of that. All right, so we need this conversion factor, and I went and looked some up. 3.248 meters. And then 1 meter is also equivalent to 3.281 feet, right? It kind of, works both ways, right? You go feet to meters, meters to feet. But I think the question now becomes, which one of those conversion factors do you use in order to convert 25.32 feet into meters? What do you think? Good, it doesn't matter, right? It never matters which one you use. Because, and the way I think of it, is I always multiply. Have you ever gotten into that thing where you're like, do I divide? Do I multiply? What do I do? Oh my gosh. The answer is you always multiply. In fact, my life is complicated enough that I have reduced it down to, I try to just take complexity out of my life. And so I gave up on subtraction and division a long time ago. Because subtraction is really just addition with negative numbers, right? And what's division? Multiplying by fractions. Okay? So there's really only two mathematical operations I need to concern myself with, addition and multiplication. So, in that sense, I can take that 25.32, and then all I'm going to do is multiply by a fraction. And I'm going to let the units do the thinking for me, in a sense. I know that I want to get rid of feet. And so in order to be able to cancel the feet, does it go in the numerator or the denominator? The denominator, right? Or treat the units like you're going to cancel out numbers, right? Or something like that, right? Okay, what goes in the numerator then? Meters. Okay, now, which numbers do we put in there? Doesn't matter, right? These two conversion factors are actually the same thing. So you pick one. If you want to put, 1 foot in the bottom, what are you going to put in the top? 0.3048. Somebody do that for me. Somebody take 25.32 and multiply it by 0.3048. Hold on to the answer. If we do it again with feet on the bottom and meters on the top, then if I put 3.281 feet in the bottom, what am I going to put upstairs? 1, right? Feet cancel. I'm left with meters. Somebody can do the bottom one or not. But did anybody get what the top one was? 717 meters. And if somebody did the bottom, I'm guessing that you got pretty darn close.
Yeah, 7.717.
Okay, right? So it turns out to be the same thing. Okay? So that's the way that you deal with unit conversions. Don't ever get yourself tied up in whether you're multiplying or dividing. You're always multiplying. You're just multiplying by a fraction. Get the units in the right places, and away you go. You can stack these up as well. If we wanted to find out how many seconds there are in a year, well, we want to know, we start with 1 year, okay? And if we're going to get to seconds, we need to have a series of conversion factors now, don't we? What's the first one, maybe?
1 year, 36, 5 days.
Okay, so we can go from years to days. And how many days are there in 1 year? In 1 year, how do I know I'm putting 1 year at the bottom? Got to cancel the years, right? I'm going to put 365 and a quarter days. Okay? Where do we want to go from days? Again, we're trying to get to seconds. In 1 day, there is 24 hours. In 1 hour, there's 3,600 seconds, because I'm bored now. And 60 minutes times 60 seconds in a minute, right? It's 3,600. And I have no idea what this number is, nor do I really care. Okay? The point is that you can go ahead and just keep stacking up these units. Go through here. I realize that all of them are going to cancel except the seconds that I'm looking for. Okay? And did anybody actually calculate it?
31,536,000.
31 million is good enough for me. Okay? So, take advantage of this ability to stack these. Remember to just always multiply and get the right numbers in the right place with the right units in the right order, and you should be good to go. This brings up a concept, an idea that's fairly closely related, and I'm not sure it's one. Have you ever heard of order of magnitude before? Yeah. Order of magnitude is a special, fancy scientific way of talking about powers of 10. So if we're into an order of magnitude to my height, I'm about 1.6 meters, okay? Then I'm about 1 meter, right? I'm certainly not 10 meters, okay, which would be 3 times higher than the ceiling, right? So order of magnitude says, I'm going to get to within a power of 10. Okay? How many people are there in the United States right now? Right? It's in the neighborhood of 300 million. Somewhere between 300 million and 400 million. Both of those are an order of magnitude. We're in the hundreds of millions. It's not a billion. It's not tens of millions. It's in the hundreds of millions. And that's what order of magnitude is all about. In physics, we use order of magnitude all the time because we don't like reality, but because we want to check and see if our answer is reasonable. Okay? But there's other places you can use order of magnitude, especially, and this is going to drive the engineers absolutely bonkers, okay? When you really only want to know sort of what the answer is, and not exactly what the answer is. Let me give you an example of this. We're going to bring an engineering major, a physics major, and an English major into the room. Okay? They're not walking into a bar, they're walking into the room. And we're going to tell each of them that they have to measure the volume of air in this room. What does the English major do? Cries, right? Okay. Because they can't remember what volume is. All right, what does the engineering major do? Measure? Like describe how the engineering major measure. Okay, I forgot my meter stick again. Describe how the engineering major would measure this room. Exactly. With lasers. Right? They would nail down the dimensions of this room down to the nanometer and then realize, oh, there's heads! There's animal heads on the walls. I got to subtract that. Because, right, that takes up space in the room and that's part of and there's students, stop breathing. Oh my gosh, you're taking up it, right? And then some engineer would probably recommend at some point that you fill the room with water and then take all the water out and measure the volume of water because that would be more precise. Right? Why are engineers like that? Why are you going to be like that if you're going to be an engineer? Why?
Otherwise, everything's going to break.
Well, more importantly than it breaking.
You're liable.
Yeah, you're going to get sued. Right? Okay? That's the one thing to differentiate physicists from an engineer. We can't get sued. Engineers have to be careful because of laws. Physicist, physics major, how would they come in and measure the room? It's about 10 meters. It's about 10 meters. It's about 3 meters. 10 times 10 times 3, 300. When's lunch? Right? That last calculation doesn't give you a precise answer, but it gets you within the ballpark. It's called an order of magnitude problem. So that when the engineer actually did the problem and found out that there was 296.37 cubic meters of air in this room, we'd be like, yeah, okay, fine. But we got lunch sooner than you did. So order of magnitude calculations are closely related to unit conversions, and sometimes you just have to make judgment calls. For example, how many cows were consumed in the United States last year to make fast food hamburgers? What do you need to know in order to make that calculation? How many hamburgers, right, were consumed by Americans. You have to make a judgment. Now, I'm sure that there's something on the internet that will tell us precisely, right? But there's some guesses that we have to make. There's 350 million people in the United States, and everybody ate a hamburger once a week. Does that seem, or is it more like 4 times a week in America? But not everybody eats hamburgers, because we got to remember all the vegetarians. And everybody under the age of 1 that doesn't have teeth. And everybody over the age of 90 who don't have to, right? Okay. So, reasonable that maybe, let's say maybe 400 million, right? I probably shouldn't write 400 million. I should write 400 times 10 to the hamburgers. Okay. And then, if we're going to find out how many cows that takes up, what do we have to kind of decide about these hamburgers? Well, okay, we've got how much meat is there in a cow? We've got the issue of how big is a hamburger. It's McDonald's, we know it's a quarter pounder, right? Burger King, we know it's a Whopper, whatever size that is. Right? So far. So if we say that there in one burger, there is 0.25 pounds, right? And then how many pounds of useful hamburger beef are there on a cow? What's a cow, Mr. Balo? Like 500 pounds? I have no idea. But I'm guessing it's somewhere between 100 pounds and less than 1,000 pounds. Does that seem reasonable? Because there's other parts of a cow. There's the bones and the ears and the bell and everything else that goes onto a cow, right? So let's just, for the sake of argument, say 400 pounds, right, in one cow. Is this calculation going to give us the answer? No, but it's going to tell us approximately how many cows, right? And in this case, it's whatever a quarter of 100 million is. 250,000 cows? Okay. No. 2.5 million cows? There we go.
100 million, so it'd be 25 million?
25 million. Yeah, I can do that. Okay. 25 million cows. Right? For hamburgers. Approximately. And I wouldn't be surprised if we went and looked up the industry trade secrets of all the fast food joints and found out that, yeah, right? It requires tens of millions of cows. Just for hamburgers. Not to mention anything else. So that's an order of magnitude calculation. All right. We need to talk about how quizzes happen in this class. This is a bit different from what you experienced before. What I want you to do is I want you to take 3 of these pages each. Pass them back, and I'll pick up the extras. Just send the extras back up. Everybody gets 3. Hopefully. Spread them out back there. You're going to hold on to these quiz sheets for the semester. You're probably going to need more at some point, and I'll forget to print them out, and then we'll deal with it at that point. What did I say on Monday about how you know when you've learned something? You can teach it to somebody else, right? So that's what my quizzes are for. They're actually an excuse for you to teach somebody else. So what I want to do is walk you through a quiz. I'm going to give you an actual quiz question. I'm going to make you work on it and do some other things. But the process of doing a quiz reinforces or gives you an opportunity to teach somebody else. That's because most often quizzes in my classes come in pairs. In other words, there's going to be 2 questions that are exactly the same back to back. The key difference between these 2 questions is that the first time you attempt the question, you're going to do it yourself without any help. And then I'm going to call time and say, all right, you're done with that one. Now do exactly the same question, but with the people around you. Why do I want you to do the question by yourself first?
You can think.
Think? In here? Yeah. Have you ever been in a class where the teacher asked a question, you're like, oh, I know that. Wait, just get. And then the idiot next to you just blurts the answer out? What happens to your train of thought? Total derailment, right? It's like, right? And you were robbed of a very important opportunity to form a physical, literal pathway in your brain, in connecting pieces of knowledge. As soon as you're given something, our brains just take shortcuts and that path never gets made, nor does it get reinforced. And so I want you to have an opportunity to do one of two things. Form a neural pathway or sweat bullets because you don't know what's going on. All right? This is your opportunity to find out if internally you know what's going on. And then I want to give you the opportunity to try and explain that to somebody else. Together, interacting, teaching, communicating. Again, reinforcing things, either getting help because you're lost, or having an opportunity to reinforce that knowledge. So, this is how we're going to do it, okay? I need you to put your name on there, okay? And right now, you're going to write down quiz 1.1 and 1.2. It's chapter 1, quiz 1, and quiz 2. And then I also want you to write down the fact that these are 2 points each. Talk about points later. And then I'm going to give you a question. Okay? Not right now. I'm just going to walk you through this process, and then I'll give you the question. I'm going to give you a question, and you're going to, preferably in your notes so that you have a record, okay? You're going to work the question. And then on this quiz sheet, you're going to write down the answer and a reason for the answer. You've got to have two things. What you've picked is the answer. Sometimes it's multiple guess. Today's is not multiple guess. And some sort of explanation, okay, for how you got to that answer. Just really quick. Doesn't have to be the full work. Right? You can do that in your notes and then just sort of really quickly give an explanation. But there are good explanations and there are bad explanations, and this is a terrible explanation. Terrible reason, right, for anything. Okay, so you'll write down whatever you do there, and then after I call time for the individual, I'll have you turn to each other, start hammering it out, and you might decide that you want to change your answer. Information you didn't consider, or whatever the case may be, you realize something, you want to change your answer. You can then, in the second quiz box, make that change. You can go ahead and write down what the new answer is and why you picked that new answer. What was it that, jogged your memory, whatever. I had the internet make this one up for me. Okay? So, just some caveats there. You do not have to agree with your group. This is still your answer. It's just an opportunity for you to correct. Okay? If you want to keep the same answer as your individual, just draw an arrow. Just draw an arrow straight from one box to the next. So when I see these, I'll just go, okay, you're just picking the same answer. I don't want you to have to redo, right? It's stupid. Okay? More importantly, if you changed your answer, you should be figuring out why. Failure analysis is a big deal in engineering and science. It didn't happen the way I expected it to, or in chemistry, I burned my eyebrows off, or in biology, I got really, really sick. Something went wrong, and I need to figure out where it went wrong so I can not do that wrong thing again in the future, right? So we're not afraid of failure in here. We're not afraid of getting it wrong. We're not afraid of being wrong, because that gives us a point to start from to expand our knowledge. So this is an opportunity for you to correct that. Okay, so there's the outline. Let's go through it. Let me give you your first quiz question. Oh, and then we'll talk about scoring in a second. Okay? So here is your first quiz. Quiz 1.1, 1.2. Again, I'm going to give you the question. You're going to think about it. You're going to work it. And then you're going to write down your answer in the 1.1 box. How many cubic centimeters are there in 1 cubic meter? Go. Keep writing as I talk. But at some point now, you're either in a total panic because you don't know what's going on, or you've got some sort of idea, answer. Make sure to put that answer on the quiz sheet, because in the future I'll collect these and I want to see that you're here to do the work. Make sure that you have some sort of explanation. It can either be a picture you drew, the math that you did, a written sentence that says, I chose this because, all right? So that's what you need to have on your quiz sheet. These tend to go pretty quick, like the individuals, I only give you like 1 or 2 minutes to kind of stew on it, and then we jump right into doing the group work. Okay, have I given you enough time to write something down on your quiz sheet? Once I call time, I don't want you changing that individual answer. I know you want to. I know you want to go back. It's wrong. You can't be there. No, leave the wrongness there. Reminder to you of what needs to be corrected. All right. What I want you to do at this point is call time. I want you to turn to each other, share your answer, and why or how you got that answer. Go. Write down any changes, right? If you didn't change anything, it's just an arrow. But if there's a change, new answer, and why, right? So you kind of want to do that while you're actively talking and teaching and getting that back and forth. Again, you're looking for where you messed up or where you did it right. Okay, both of those are good. Like, oh, I nailed this versus, okay, I forgot about blah, blah, blah. Right? Those are really important notes to you for your future studies. Okay, so does everybody have a group? So you should have an individual answer, 1.1, and a group answer 1.2. Right, on your pages. All right. We will determine the correct answer by voting. Just to maintain the illusion of the mind. So, by a show of hands, how many of you say the answer is 1? 10. 100. 1,000? 10,000. 100,000. You sensing a pattern? 1 million. 10 million? Do I hear 100 million? Billion? Trillion? So, the majority, or at least most people, so we were divided between 100 and 1 million. And the majority, or at least the larger population, seemed to be in the millions category. So, somebody from the millions group, you want to give me a reason? Explanation? Go for it.
So I'm not 100% sure, but
That's
I think
okay.
it's because if you have a cube or something with a 1 by 1 meter by 1 meter by 1 meter, and you're multiplying the 1 meter, it's the same thing as multiplying 100 centimeters by 100 centimeters by 100 centimeters. It comes out to 1 million.
I apologize for my lack of artistic ability. That's supposed to be a cube. To an order of magnitude it is. Okay, so you went for a visual. Did you see the cube in your head? And okay. Did you do it a different way or same way?
I just knew that if it's cubed, you multiply it 3 times because it's cubed.
Oh, so you were like, okay, I need to start at 1 cubic meter. And so conversion factor wise, every meter has 100 centimeters in it.
Yeah, cubed.
And so I just cube it like that, but that would be 100.
No, I cubed that conversion factor.
What? You have to cube the whole enchilada? Yes, because you got to do 100 centimeters for every meter 3 times. Right? Why do you have to do it 3 times? It's cubed. And which you get cubed the whole thing, which cubes the centimeters, cubes the meters, and cubes the 100. And what's 100 cubed? Okay, so for those of you that said 100, where did it go wrong? Be brave. It's okay.
Didn't cube it.
Didn't cube it? You just sort of thought maybe that, okay, well, since 1 meter is 100 centimeters, then 1 cubic meter is equal to 100 cubic centimeters? Right? You broke math right there.
I think where I went wrong was I equated it 1 meter was 12 centimeters.
Right.
That's where I messed up.
you went to inches. It's the imperial system getting you wrong.
Yeah.
So, yeah, you want to be,
I mean, I did think about cubing it, but obviously because I went to inches, it didn't work out.
Oh, I hate the imperial system. All right. So, what's the takeaway here when it comes to working with conversion factors? Be careful. Now, for those of you sitting there in the 100 groups going, well, you cheated, Mr. Ben. You tricked me. You didn't give me the right conversion factor. It's in the book. Okay? Just process everything. I even showed you how to stack conversion factors, right? But I also want to point out here that visually, perfectly good. Mathematically, it's a great way. Okay? These are all, if you did something like this on an exam, I would take either of the ones on the top there as correct answers. Okay? There's more than one way to skin a cat in physics. And so as long as I can kind of understand what you're doing, we'll be good. So I like visual approaches. I like math approaches. Well, I don't like it less in the math way. But that's just me. All right. What do you do about the scores on your quiz sheets? Who scores your quiz sheets? You do. Okay? So some of you are thinking, oh, cool, I just got 100%. Okay. So 2 things here. I give out about 200 points during the course of a semester for quizzes. Okay? But I only count up to 50. So as soon as you hit 50 points on your quizzes, you have an A. on your quiz score. That's 5% of your total grade. Okay? So I stopped counting at 50. Chances are by the end of the semester you're going to have 80, 90, 110, whatever. Okay? 200. Fine. Okay? This isn't about the points. It's about thinking. It's about having an opportunity to communicate, to check and see. Ideally, as we do these quizzes, the notes you're writing down for this class are things like, I didn't get that unit conversion thing. I need to study this. And then when you have time to sit down and study, you're pulling that note out. Okay, this is what I'm focusing on. Or, we did the unit conversion. I remember that. I did pretty good. Just do a real quick refresher on this. And I'm good to go. That kind of note-taking is golden. Because I've got everything else written down for you. And it'll be available on the interwebs. All right. We are going to jump right into chapter 2. But before I do that, I actually want to talk about something else that I learned about this summer, and I'm going to convey to you. This is something I realized that I always knew about, but I never knew the name for it. So for 18 years, I've been actually doing techniques in my classes to help my students with this. But you're the first class that I'm going to directly teach for the next 5 minutes about something that has nothing to do with physics and everything to do with your learning. Why are you here? To learn how to learn. When I talk to engineering firms in the valley, when I talk to pharmaceutical schools, when I talk to graduate schools, I ask them, I teach freshmen and sophomores and they're going to transfer on to your institutions. What is it that they need to know when they graduate? The answer is never physics, chemistry, or engineering, fill in the blank. It's always, do they know how to learn? It's some variation on, can we teach these people something? Can they learn on their own accord if we give them information? And can they write a decent email? That seems to be cropping up more and more, right? So, learning how to learn is vital. And I do lots of things in my classes that you don't realize, like this whole quiz thing is all about you learning how to learn. But I want to talk about something specific that I learned about this summer. And it's called stereotype threat. And I think you know what a stereotype is. Go ahead and give me a stereotype. Go ahead, don't worry about being politically correct.
Women drive badly.
Women drive badly.
Asians are supposed to be smart.
What's that?
Asians are supposed to be smart.
Asians are smarter. Go ahead. Don't be afraid. Black people do sports better. Women can't do math. Old people can't remember things. Young people are stupid. The list goes on and on, doesn't it? These are the stereotypes. Stereotypes are a human being's way of being able to quickly categorize something and move on. And they're often not fair, and all of them are false in some way, shape, or form. And stereotypes can go either way. We humans tend to concentrate on the negative stereotypes, but there are positive stereotypes as well. And a negative stereotype wreaks havoc. Positive stereotypes wreak an opposite havoc. Stereotype threat, that's what I learned about this summer, is when we recognize a stereotype. You probably felt it almost instantly when we started listing them. What did you feel when we started calling out some of these? Targeted. Anxious. You wanted to prove it wrong, so you were like, stereotype threat is the emotional response that someone has to any stereotype. Whether it's overt, somebody says it in front of you, or it's implied, somebody's looking at you funny, and you internally have your own stereotypes that you may not be aware of. And so one of the things that I want you to start thinking about is this concept and idea of stereotype threat and how it has a real, emotional, and physical response. Because, I brought, where did I put it? Brought the proof. Women perform worse on math tests when they think the test will produce gender differences. So they gave out a math test and they told the women that there was a gender bias. That's all they said. There's a gender bias on the exam, and all the women did worse. Does that mean that women are worse at math? No. It's totally false. And yet, the stereotype threat was enough for them to measure a difference on their test scores. White men perform worse on math tests when they think they are competing with Asians. When a classroom was told, your scores will be compared to those from people in fill an Asian country, the white men who took the test did worse than exactly the same test where they were not told any information. The tests were not different. The populations were big enough. That's stereotype threat right there. Black students perform worse than white students on the GRE when they think the test is measuring their ability. But when the black students are told that the test is not measuring their ability, they perform just as well. Black athletes do worse than white athletes when they are led to believe that a game of miniature golf tests, quote, sport strategic intelligence. But when the test is framed as a measure of natural athletic ability, the white athletes do worse than the black athletes. It's just crazy. Does anybody want to know about female chess players? Female chess players perform worse than male chess players when they are aware that they are playing against a male opponent. When they are falsely led to believe that they are playing against another woman, they perform just as well as the male player. What does this tell you?
It's in your head.
It is in your head. Self-fulfilling prophecy. So what do we do with this kind of information? I got a lot more of this if you're interested. Okay? What do we do about this? There's going to be a moment, and it's going to happen either very soon in physics, or it's going to happen right before or right after the first exam, when you're confronted with being wrong, having a bad grade, frustrated with the homework, and that begins a cycle of, I can't do this. For some of the women, it's going to be, oh, well, they must be right. You may not think that in your head in a sentence, but you feel it. You've heard it before. Okay? And now it gets reinforced. Or, I'm not good at sports. And so when you go out and you fail swinging the bat or throwing the basketball or whatever, it reinforces. And it's all about the emotional response you are having to that given stimulus. And so, to put it very succinctly, there is power in positive thinking. Because the stereotypes are false. There's a reality. I'm short and somewhat fat, right? I'm just not going to be the greatest basketball player in the world, right? But that doesn't mean I can't improve my skill. The fact of the matter is that all brains, all the time, can change. They're not frozen. You are not your gender. You are not your race. These are all important things that make you you, but they don't affect how you learn or your ability in the future. What happens in the past has stayed in the past, and your brain has a magnificent ability to correct and to move forward. So I want you to be aware of that. I do a lot of things in my classes to support students, especially minorities, because there are all of these things. You've got culture sometimes that's against you. The number of students I have come to me that tell me, well, my family wants me to drop out of school so I can go back and work for the family. It's incredible, some of the pressures that you are under. And I want you to know that the pressures are real, and our response to them are choices that we make. So I want you to just kind of put that back in the back of your mind, because as we get closer to the first exam, I'm going to be reminding you of how awesome you are. You've made it this far, right? You've made it through Math 5A at the very least. You're in a career of your choosing because you had some interest in there, and you are going to make an incredible impact on the world. We can remember that we can change, that we are better than what other people or even our own brains tell us that we are. Then I have lots of hope for you. What do you think? Sound crazy? It's okay to say yes, right? But I want you to think about it. Okay? Do a little bit of research on your own, maybe. Stereotype threat. You type that into a browser, and you're going to have your eyes open. All right. Chapter 2. Just remember, we can do this. What? My favorite stereotype? Physics is for smart people. You want an example? I am not smart. Okay? I like physics. Over the years, more than 2 decades, I now sound smart, but it was a fight. Successful physicists are stubborn. We don't let go. Difference. All right. I know that some of you didn't get into chapter 2. We haven't really talked about the book yet. We're going to do all that tomorrow. So normally, what I would do is I would jump straight like into the end of chapter 2. I'm going for the things that I know are going to give you difficulty. That means there's other things in the chapter that I'm assuming you can get just by reading, interacting with the homework. So really starting in chapter 3, that's what I'm going to do. Kind of babying you here at first. But as an example of something that I would assume you can get from the reading, we need to have a talk about the difference between average and instantaneous. I'm going to do this in the context of taking a drive to Los Angeles and plotting that drive on a position versus time graph. Again, this is something also in chapter 2 that normally I would not spend time in lecture because it's fairly basic and you should be able to get everything you need to know out of the book. Forgive me for the violent analogy here. Physics is a lot like a minefield. Somebody is telling you that you have to run through the minefield to get to the other side. You don't know where the mines are. Well, what do I know? I know where the mines are. Why do I know where the mines are? Because I've been through the field, right? Okay? And I stepped on a few of them. Okay? And you will too. But I'm out here going, there's a mine there, go around it. Go this way. Don't go that way. Right? I'm trying to guide you. You have to walk through the minefield. You've got to go through all the steps. But at certain points, I'm going to jump in and say, go this way, go this way. Right? And so that's what I do in class. I point out the mines. Okay? So that we can skirt around them and there isn't too much trauma. If you step on one, I'm there for you. I have emergency medical training. Do this, right? But best to not step on the mines. So this would be something that I would not consider a mine. Again, I'm doing this just because I know we're still sort of funky with our book. Let's leave from here and let's talk about what happens to our point in space as time goes by going to Los Angeles. The very first thing we have to do is pick a coordinate system and an origin of coordinates. So where is 0? Right here. That spot right there is 0. Okay? So we'll call going to Los Angeles positive, although in my case that would be a very negative thing to do. And what would that look like if we were to consider our position as a function of time? So we headed towards Los Angeles. You take your arm and maybe give me an indication of what it might look like on this graph. I like that one. Right? The first step is we got to get on the 41, right? What's the speed limit on the 41?
90. 65?
65, okay, right? So we would draw a line that shows that our position is increasing. We're getting further and further away from where we started, right? In a certain amount of time. After the 41, the next highway would be the 99. And what's the speed limit on the 99? About 7,000 miles an hour. Okay? Because if you're not going 7,000 miles an hour at the 4199 Jensen interchange, you're dead. Right? Every truck, every car is going to just run you over. Now, why did I make this steeper?
Accelerated.
It's faster. The speed limit's 70, right? Okay, and it's so. But I made it. Our position. We're getting further and further away quicker, right? Time's going by, but we're changing our position more rapidly. Okay, and then after the 99, you get to the 5 and the Grapevine. You learn how many people in the valley don't know how to drive in the mountain. And then you're coming down to LA and you hit the 405. Tell from some of your reactions that you've been there and you understand that Highway 405 is LA County's designation for the largest parking lot. Okay? Because when you get on the 405,
You don't go much.
you should have your 3-day survival kit with you. Food, water, entertainment, sleeping bag, gun, whatever it is you need in LA, right? But you are not going anywhere. Time is passing. Your life is flashing before your eyes. Because that's really all it can do. Think about that. People say, my life flashed before my eyes. I'm like, yeah, it started at birth. Why is that line flat? Because your position isn't changing. Time is going by, right? But the position is not going up or down. We read from this graph, right, what our distance is compared to what time has gone by. That steeper section tells me that we were moving faster. And now you're like, oh, what about the velocity and the slope of the line and all this kind of stuff. Okay, we need to talk about all of that. Right? Because I want to know, how do we... Okay, I'm about to write down some mathematical symbols. Okay? And here's one thing that I know you've been taught to do throughout your entire scholastic career. As soon as math happens, you turn your brain off. Right? Okay? Math teacher's up there, right? And your brain shuts down. Okay? Jaw hangs open, right? So let's try not to do that. Because we're using math as a foreign language. What does this mean? Delta X. It means change in a position. Literally, we take where we ended up and where we started, x final minus x initial, and take their difference. So, if I want to talk about how my position changes in time, I have to have certain changes in time, right? And this is going to be time final minus time initial. What do we call this thing? Nope, not yet. What is a change in position versus a change in time? It's velocity. Speed, velocity. We won't get into the whole direction thing yet. We'll do that next chapter. But here I have a symbology, a way of writing down a relationship. My speed, my velocity at any given time is going to be how much my position is changing versus how much time is going by. That was a long sentence, wasn't it? Written in a very small, compact form. Mathematics was the original compression algorithm. It let you take really big ideas and write them down as really small things. All right. Well, what happens if I change my velocity in time? I get an acceleration. So the difference between average and instantaneous. What does that word instantaneous mean? It's got that word instant in it, doesn't it? Right now. Not now, but now. And in math, we can force those deltas to get itty bitty teeny tiny. How do we do that? Calculus. Specifically, limits. Don't panic. Do not panic. We are probably never going to do a limit in this class. Okay? Because all of our limits are like, well, I'll just make it small. You went through all that horrible math of limits and things, like when you have a limit up and a limit down and a limit sideways and you combine the limits. Oh, man. Right? But if we kind of take the limit as these delta t's and x's and things approach 0, right? You're gonna, okay. If we divide if we divide by 0, we do delta x over 0, what are we gonna get? No? Undefined. That is such a cop-out. Oh my gosh. Undefined. What do math teachers mean when they say undefined? They mean that there is no mathematical way of, there's no function that is defined that can perform that operation. Total BS. Okay? Because when you divide by something that's smaller and smaller and smaller, what happens to your fraction? It's bigger, bigger, bigger. And so the answer is, when you divide by 0, you get infinity. And infinity is a really cool place. It's kind of a sort of turquoise blue. Okay? It's really close. It's got nice clouds. Don't be afraid of infinity. We get to use infinity a lot in physics. It's a really convenient place to toss anything you don't want to deal with. Okay? Infinity's great. But more importantly, as we take these limits on these deltas, okay, our symbols change. So instead of a delta, it's going to be a what? Dx. Greek delta, which meant some sort of broad interval, when forced to the smallest possible thing it can be, indeed, the very instant turns into the letter D. Now, I'm guessing that your math teachers didn't stop here. Right? They immediately and horrifically probably did this. Right? Or T or anything else in the bottom, right? Okay. What is that? The derivative. What's a derivative? Slope of the line. Kind of beat up some math teachers. What did I just write down? Be careful. What did I just write down? A change in x over a change in time. That's what I wrote down. A change in position over a change in time. The difference being is I want to talk about it now as opposed to later. Now, have I taken away all the magic of the derivative? Can I do this and still get the tangent line and the slope and the velocity? Yes, all of that happens. But don't ever forget that a derivative is a ratio of two changes. Something is changing compared to something else. Try not to make it any harder. It isn't. Remember, calculus was made for physics, not the other way around. As much as the mathematicians want you to believe that. Not true. Let's say that our trip to Los Angeles is 200 miles. And I'm using the imperial system at the beginning here because I want you to feel comfortable with doing the numbers in your head, but I'll start switching to metric probably by chapter 3 or 4. Let's say it's 200 miles, and it took us 4 hours to get there. How fast are you going? 200 miles, 4 hours. How fast were you going on the trip? 50 miles. How'd you do that? Take 200 miles, I divide by 4, I get 50 miles per hour, right? Okay, savor this moment. You did physics in your head. Right? Don't forget that, because We're about to introduce some other things, right? And we're going to introduce numbers that aren't easy to do in the head, and we have to have a method for dealing with that, right? So 50 miles an hour. Were you going 50 miles an hour the whole time?
No.
Right, okay. But that's an average, right? If we wanted to look maybe at only the portion on 41, then our delta t's would only have to be the time that we were on 41, right? Correspondingly to delta x as well, we were on 41. But, you know, as what happens on the grapevine stays on the grapevine, my kids would usually just throw up, right? In which case, I had to pull the car over, and my instantaneous speed for certain portions of the grapevine was 0, right? Because I was chucking kids and car seats and clothes and everything out of the car, right? So it's fine. So our speeds can change from instant to instant, but we can talk about averages, or we can talk about what's going on now. And symbolically, we can write down the fact that I want to talk about right now with D's. Whereas if we're going to spread it out a little bit and just talk about an average, we'll go ahead and use deltas. Okay, let's, I already did that. Let's segue and start laying down what we're going to do to help you with dealing with the universe. I'm about to write some equations on the board. I'm going to write them on the iPad. We'll see why later. Okay? But I'm going to throw some equations at you, and I'm going to guess at what you think they are.
Congrats.
Good job. No, actually, that's not what I was talking about. Okay? Oh, I need to double check notes and make sure I get the right symbols that your book uses. Those symbols are a big deal.
Down.
Forgot to look them up this morning. You're going to see different symbols, like if you go to the internet and you look up answers on Chegg or something like that, you'll see people using different symbols to mean the same thing. You really need to get over that, right? You know, somebody might use X for a position, and then somebody else might use S, the letter S. And you just have to be able to go, okay, fine, it means the same thing. Don't get caught up in the symbol. I will try to do what the book does for its symbols, although sometimes we'll deviate because I think they're stupid. Okay, this is an equation, right? It's relating some things together, but like all math equations, it is a sentence. It means something. So, you can read right off what this says. Let's try this exercise together. What is V? Be careful. It's different than this one.
Initial.
This is the initial. V naught is what we say here. N-A-U-G-H-T is an old-fashioned word that means 0. Okay? Some of you, like I was born in the 70s. Okay? When we've had people born in the 80s, the 90s. We had people born in the teens, 2010, right? And they're not here yet. If you were born between 2000 and 2010, what is your decade called? The naughties. All right. So, what is this? The final velocity. The velocity you end up with is, or comes about because of, the velocity you started with and how your velocity changed
Over time.
in time. What did you say, Mr. Neal? The velocity you end up with comes about because you had some to start with, and it changed in time. So that's
So it's a constant?
can be. More on that later. We'll treat it as constant for now. But I want you to start seeing these equations in your book as having real physical context and real concept behind them. All right, there's another one. That delta x right there, what's it trying to say? Change in position, or in other words, how far you go depends on, or is, or comes about by how fast you're going and how long you did it, and how fast your speed is changing and how long it takes. Yes, I know there's squares and halves in there, but the concept and idea here is that I'm looking for how far. And that how far depends on what I started with, the speed I started with, and how that speed changes. What does this one say?
Final velocity.
How fast I'm going at the end depends on how fast I started with and how much my speed changed and how much my position changed. Now, I know there's squares in there, right? But more importantly, I'm getting ideas about how these tools work. Because what I just gave you is a toolbox. There are 4 things you need to build a house. What are they? Boards, nails, so you need materials. Okay, what else do you need? Labor.
Capital.
Okay, well, that's part of the materials. Permits, materials. Time, material.
Location.
Material.
A plan.
I need a plan. Okay, and you need tools. First formula on top is what? I didn't hear the end of the question. No, not integrals yet, but I am going to get there. So the question was, is basically, can I get from this equation to this equation by doing calculus? The answer is yeah. Okay, so we'll get there. Did that answer your question? So you need materials, you need labor, you need a plan, and you need tools. These are tools. Oftentimes students think that this is the entire house. These are just tools that you use to build the house. The plan, the labor, the materials, and the plan, that all comes from you. The materials are usually the problem that you're given in physics, right? And yes, it's all word problems, okay? The labor is you, right? And you're going to reach for tools. But you don't reach for tools first. You do a plan first. You got to have an idea of what the house is going to look like. Because if you're trying to drive nails with a screwdriver, you're doing it wrong. A lot of times students come to me, well, Mr. Balo, I'm not sure which equation to start with. Okay. Problem right there. You don't start with equations. You make a plan. And the problem-solving method, here's the path to expertise and thinking like an expert. Treat every problem as the same problem. I know. One's going to be on velocity, another's going to be on acceleration, another one's going to be on momentum and Newton's laws, and the details will change. Every building looks different. But they all have plans, they all have labor, they all have tools. If you can start seeing every problem in Physics 4a as the same problem that takes the same steps to get through, your life is going to be so much easier than thinking of it as disconnected problems. Look for this in every problem. And this is what I do all the time in lecture. I model this, all that kind of stuff. This is your plan. And your book and other books and the internet, I have seen plans with 18 steps in them. I can't remember more than 3 things in a list. Okay? And so I broke my own rule by having 4 steps. Right? Okay? But I had to boil this down. Because if I didn't boil this down, I was going to be in big trouble. Okay? Your book and other books will even go like, well, here's the problem-solving method for chapter 2. But in chapter 3, here's a new problem. It's exactly the same thing. They just use different words. Right? Don't fall into those traps. Think of the problem-solving method as the problem, and everything else will just fit into it. The steps, I think, are more or less explain themselves. Visualization is all about getting a picture either in your mind or on paper. Sometimes it's not visual at all. Sometimes it's just making lists and writing down information. What do I know? What do I not know? What am I looking for? You've been given a lot of information in a problem. Categorize it in a way that makes sense to you. Again, I haven't reached for an equation yet. Okay? I'm just trying to figure out the parameters and limits of what I'm being asked to do, what's going on. Maybe I'm trying to see what's going on in my mind. There's lots of different ways to visualize. But it's this step of confronting the information for the first time and sorting it and organizing it. The strategy, that is where you make a plan. I want to find out how far the car went. That's where I'm ending up. But I've only been told what its acceleration and time and initial speed is. So I know both ends. I know where I'm starting and I know where I'm going. How do I get there? That's where your strategy comes into play. And in that strategy, as you develop it, you're going to reach for a tool in the toolbox. Maybe more than one. Notice, we don't reach for the tool to begin with, right? We categorize, we visualize, we come up with a plan, and we select appropriate tools. What do you think happens in the do it step? That's where Nike comes and sues me. They said just do it, and they're wrong. You don't just do anything. You do it. Do or do not. There is no try. And then check it. That's order, magnitude, and a bunch of other things come in to make sure that what we have makes sense with our plan, with our visualization, and with the world in general. Master this, and you've nailed every test and homework problem in here. The rest is details. This is where mastery lies. Okay? I'm going to stop there only because I don't have time to continue on. What's going to happen on Monday? It's not Labor Day yet, right? What's going to happen on Monday is I'm going to put this back on the board and we're going to start doing examples together. I'm going to model the problem-solving method for you. I want to say this, though. You're not required to do my method. You come up with a method that works for you. But make sure it doesn't have the shortcut of starting with the equation. That is the worst possible trap you can get yourself into. When am I seeing you next? Tomorrow. Did you notice that I did not take rolls? On purpose, because I'm doing all the add drops tomorrow. So, be at the lab that you are trying to get into. If you're not on the wait list, I don't have room for you.